In this video, we're going to look at the normal approximation to the binomial distribution. So we're going to dip back into our binomial distribution, and here's a picture of a binomial distribution here, and you can see that that looks a little bit like a normal curve there. And if I change some of the values of n and p, it should change the distribution. So it moves, the p value shifts it left and right, and the n value changes the size of the little sticks. Okay, so you can see as I move that, that looks very much like a normal distribution. If we put a curve through that, if we drew a line or took a function to fit it, look at that. That's pretty much normal. And that's the idea of having a normal approximation to a binomial distribution. We're going to model the distribution for the binomial distribution using the normal curve. Let's have a look at it a little bit closer. So this example one here from GeoGebra, thank you very much to Marlin who made this. You can see that we've got the equation for a normal distribution curve here. So our standard deviation at the minute is 3.24, and our mean up there is something tiny. I can't see that. Let me see if I tap on this, can make it bigger so we can see. There it is there. So our mean is 35. And you can see that we've got the sticks for the binomial distribution and the green function curve over the top. And if I move the n value, you can see that the shape of the distribution moves. Okay, the center of it moves. And if I move the p value, you can see that it gets larger and smaller. But you can still fit a curve there. And what you're finding is, if I pause just here for a second, so what this is demonstrating, and I'll get you to play with this if you go to this website here yourself. So our n value is currently 35 and our p value is 0.73. Now it says here that if we take our n value and our p value, we multiply them together and we get 25.55. And I don't know if you can see it, but that value there for the mean, so the formula for this green line, in fact needs that value to be the mean. So our n times p gives us our mean. Let me say that again. This is our n times our p gives us the mean for the normal distribution. And if we do the same thing for our standard deviation, what we've got is a big square root thing. This is our n, that's our p, and then we multiply by 1 minus p. And I'm not sure how much you remember about your binomial distributions, but this is the mean for a binomial distribution, and this is the standard deviation for a binomial distribution. So you just make the two of them equal to each other. So if you copy down that URL, and I'll just get rid of that thing there, you can have a play yourself and see that that's actually how it fits. So what does this mean for questions? Well, it means the guidelines go if n is sufficiently large, and a rule of thumb for being large enough is if you multiply the n value and the p value for the binomial distribution and you get an answer that's bigger than 5, and then you multiply that by q and the answer is still bigger than 5, then you can use this binomial, this normal approximation. And all you do is you use the n and the p value from the binomial as your mean in your normal distribution, and your npq value from your binomial as your standard deviation. The questions will have to tell you to use normal approximation. Okay, they can't. If they want to see normal approximation, then they need to tell you to use normal approximation. Otherwise, the answer for just a large binomial is completely acceptable. Okay, so if you have a look at the questions in the exercise itself, you'll see right at the top of the exercise, this is what you'll see. It'll say something like use a normal approximation. So for the normal approximation, you can replace your mean with NP and your variance with NPQ. Let's have a look at an example. We'll do it binomially and we'll do it as a normal approximation and see what we get. So here's a question. 1,000 students were asked if they preferred vanilla ice cream over all other flavours. In the general population, 30% of people prefer vanilla. Find the probability that between 270 and 330 people in the sample prefer vanilla. We'd happen to prefer vanilla. Anyway, use normal approximation. So we know our n is 1,000, our p is 0.3. So we check our NP and our NPQ. When you multiply those values together, this is what you get. Both of those values are greater than 5, so it's okay to use a normal approximation. So if we do it the normal approximation way, our upper limit is 330, our lower is 270, our mean is NP, and our standard deviation is the square root of 1,000 times 0.3 times 0.7. You can actually put that equation into your CAS calculator. It will work. When you do that, you'll get an answer of 0.96, so the probability that they're between 270 and 330 is 96%. If you do it using binomial CDF, same upper and lower, your n goes in nicely, your p goes in nicely, you also get 96%. Now the reason that we used to do this normal distribution stuff is it's a little bit more difficult to calculate these large binomial distributions by hand. Okay, so we used to have to do this by hand. So imagine raising 1,000 to the power of 270. Difficult. And so we had our table of values for normal distribution, and that's why we did it. So the only reason that they would ask you to do this in the exam is to test if you know that you can in fact model a binomial distribution with a normal distribution. And like I said, they will have to tell you to use it.